around this? Or? No.
Okay.
MC approach.
So next is Peter Willendrup. There you go.
Thank you, Pete. So some light entertainment standing between yourselves and coffee, and I'll try to stick to the 15 minutes. There's a pointer here. So I'll talk about the MaxDash code and what I will do. If I can, no? Okay. I'll have to go by keyboard. What I'll do is, for those of you that don't know the code, there'll be a quick introduction to what the code does. Then I'll give you a brief overview of 25 years of history of this project, and then I'll drop down on highlights from the latest release. So what is MaxDash? Well, it's quite flexible general simulation utility for neutron scattering instruments experiments. The name comes from being designed to do Monte Carlo simulation of triple axis spectrometers, which is one type of neutron instrumentation. We've moved far beyond that. If you counted instruments in the code, it would be called MaxStuff because it's time of flight spectrometers, but I think, well, MaxDash might sound strange, but MaxStuff sounds even stranger. So we'll stick to that. It's a common effort of DTU Physics and European Spallation Source, where I'm seconded to myself. The ILL has been involved, and PSI, University of Copenhagen, and so forth. The first release was in 1998 from Risø National Lab in Denmark. Luckily, a computer scientist was involved, together with Kim Lefman. So Christian Nielsen was the guy that came up with the code generation mechanism that we use. Well, we're a small team. The main effort of it is actually based at the ESS DMSC at the moment, where I share an office with Mads Bertelsen. We actually have a younger sibling called MagXtrace, which is the same technology but for neutrons. So we've basically, the physics models govern the transport of neutrons in matter. In X-rays interacting with matter rather than neutrons, but otherwise, technology-wise, it's about the same. Currently, it's Emmanuel Fahy at Soleil and myself that do this work. But I'll focus on the neutron code here because that has the most impressive age in that sense. So over the course of 25 years, we received quite a number of different types of support, mostly from the EU, but also, let's say, facility construction projects, the ISIS Target Station 2 project in the UK, and the ESS project in Lund, and so forth. So we're highly embedded in especially the neutron landscape in that sense in Europe. So what does it do? It's a simulation toolkit for instruments at a neutron facility. So this means we have to start with a source of neutrons. So this could be a reactor, like the ILL next door, or a spallation source like SNS in Oak Ridge, Tennessee, or whatever you like. I say neutron source, but actually what I describe in my MaxDash source is just the output of the neutron moderator. So you have to kind of imagine that clever guys running a multi-particle standard model, particle propagation code like MCNP or Fluka or Shankt or whatever. They did some work initially and characterized moderators, and then I take the output of the moderators. So that's what we start by. Then we, of course, include various types of neutron optics that tailor the beam for the different types of science. And this then covers, of course, reflectometers, small angle scattering, diffraction, spectrometry, imaging, whatever you like. And we have models of everything. You can also put in model samples. So you put in a powder in your diffractometer, and out you get a diffractogram that qualitatively and actually also numerically, more or less, corresponds to what you would measure at the beamline. Of course, all matter scatters, and this means if you have a sample environment, you would actually really to assess what you would often on a beamline call spurionic scattering. So little features that have structure in your measured signal. If you'd like to assess what these are, you actually have to model that somehow. And we have a sophisticated system for that called the Union subsystem that, can model the sample as well as the sample environment and any kind of multiple scattering around in that geometry. We run on CPUs and we run on GPUs. Admittedly, that factor of 600 there, that is for an ideally parallelizable problem. So the factor of 50 or something like Vincent was saying, that's also what I find in actual applications. Okay, and we are vendor locked in because I'm using what is called OpenACC, which is in maturity sense only available through the NVIDIA compiler. Okay, so MaxTas and MaxX-trace are Monte Carlo ray tracers. In a very naive picture, this is what they do. You emit particles under random starting conditions at the source. They are ray traced through space, and they will eventually meet other objects. If these are complex enough that you need stochastic processes, etc., you pull in some Monte Carlo again, and then you can measure what happens at different points in the instrument. For newtons, of course, gravity plays a role. If the newtons are cold enough and the instrument's long enough, you will actually see the beam having an effect of that. So this has to be taken into account. But other than that, it's a sort of, ballistic throwing a ball through the air in combination with billiards, meaning reflectivity on surfaces. That's more or less what it is. But put together, it can do more complex things, of course. So the way you interact with this is that you have a geometry at the upper right up there. You have a series of components. This you assemble in our own domain-specific language. And from that, we generate a C code, little bits and pieces of components that are actually contributed by people from the community, many of them, are pulled together, and then we generate one C code and a corresponding binary from that. And this you can, that's basically the story about that. It's very portable. It ran on an iPhone that was rooted, of course, to do that, but cannot recommend it. Not very efficient, but just a proof of principle, I had to do that. And then all the way up to, thousands of CPU cores or GPU cards. A main point here is that if something is missing, you have a chance to write it yourself. Yes, I think I'll almost jump here. Well, okay, so the user experience is you either pick an instrument from our example suite or you write one yourself, you launch a simulation and you look at the data. That's basically the workflow of it. Could look something like that. So on the left is our classical GUI. And you see in the browser in the middle, that's a 3D visualization of some small angle scattering. You have histograms created from that, and basically that allows you to analyze what is going on. We also provide what is called MaxTas script, which is a Python API to the same language. So you can use one flavor or the other, whatever you like. So this, one of the messages here is that writing new components for MaxTas or understanding the existing ones is not very complex. And for that reason, over the course of time, we got 350 components in total. And out of these, 30 to 40% is actually not written by people on the development team, but instrument scientists, etc., around the world. Yes, so that's more or less over the course of time, a linear growth in the number of components. And as a kind of, you could argue, integration test, we have instruments that use these components, of course. And this means 250 of those. Running in nightly tests, so we know that they, we don't mess up too much. So a bit of CI has ended in there as well. Yeah, I'll just skip across that one, I guess. Okay, anyway, analysis of what our code is says that we have a lot of PostScript. Well, That might be because we have our manuals in the same repo. So I think that's an outlier. AMPL, I guess that is a misconception of our DSL. I don't know exactly what AMPL is, but anyway, I would think that's our own grammar. 5 minutes left, that's excellent. That's a very brief look of history over the 25 years. So you can see various things that entered in here. I came myself in around 2002, so I haven't been there all the time, but quite a bit of the time. During that course of time, support for different operating systems, MPI added, support for HDF and Manted type output files, various kinds of other things. GPU came in the early 2020s, and so forth. A last few words on new things. We are now on ContraForge, and that actually now forms the support basis for non-Unix operating systems, non-Linux operating systems. So if you download my Mac installer, that is actually the Contra package just embedded in a thin shell. And we'll do the same for Windows. And then, especially due to hard work from Emmanuel Fahy and colleagues at Soleil, there are now official Debian packages for both MaxDAS and MaxXtrace. And we really have a CI system in place that means that I can do a tag on GitHub that will result in my new binaries. So that's supposedly more agile going forward. One new thing here, so that's what classical MaxDAS simulation would look like in our Python viewer here, which is PyQt-Graph. One new thing is that you can, by the click of one button, you lift that into to Jupyter, if that's what you so prefer, and you get the same output there. Another, let's say, route to more easily interpreting your simulation data, that is that I can now spawn some Nexus viewer, and I typically, on Conda, for instance, I depend on Nextp for that, which is a simple interface with a lot of flexibility to do little fitting and other things. I think this will become popular. We've modernized the 3D rendering. So this is, it's actually, there's some React in this as well. It's WebGL. There's a small server, Vite, which is a development server for JavaScript. And 2 minutes, I'll speed up. We have solids and transparency, which is new. And well, it all looks nice. You can look around in that, and there's both a 3D and a 2D version of it. And at the end, we historically had releases once per year, and we're really meant to go more agile with this. So this is coming. We have a pull request only main branch now, so no more last minute hacks. I mean, real code reviews has to happen. And we probably want to expand on the collaboration with people around, so formalizing the MaxDAS collaboration in that sense. I think that is actually where I'll cut it short. So maybe I'll drop these saying thank you and just browse through quickly and say that I owe thanks to a lot of other people, as well as users in the community, of course. That's what I had. In time for coffee, at least. Yeah.
So do we have any questions here? Work for you? Yes, sir.
So thank you, excellent talk, very interesting. And I wonder, did you think that your system could be used for teaching to let students do some virtual experiments?
Yeah, we already have a bit of that. Unfortunately, it's not as open and accessible any longer. But I'm guessing it will be again. But there's a system called it's called Pan Training, and under that there's an e-learning system that actually has this in the back.
Thank you.
Thank
So
you.
that's it for you. Yeah.
Thank you.
Let's thank Peter again.
Merci
And
bien.
then I'm assuming Andy has.
Just to say, if you sign up for a visit now, please go straight up to the first floor, and you'll meet them. Yeah. So you don't drink coffee first, yeah, for visit.
That was fast. You just.